Okay, that's base classification methods. We only discussed one method. The other method we're going to talk about in the next chapter. Rule-based classification. This rule-based classification is very it's closely related to decision trees. As we have seen before, that decision tree, we can, from decision trees, extract if-then rules. So definition for rule-based classification systems is that this system's model is a set of if-then rules. So for example, if age is young, student is yes, then by computer is yes. So this rule always have antecedent, also called precondition, and then rule consequence. So whatever after then is rule consequence. And here, all the conditions in the condition, the precondition part is conjuncted, so it's and together. So this is the if-then rule, one if-then rule. A rule-based system could have many if-then rules. And those rules can be just enumerated one by one. It could also be prioritized and created, formatted as a decision list, as what is mentioned here. When we have a rule, when we need to learn the rules, we need to have a way to assess the quality of the rule. There are two commonly used metrics. One is called coverage, the other is accuracy. Coverage is number of tuples covered by this rule. Correct is the number of the rules correctly classified by a rule. Then we can define, based on these two ends, we can define coverage and accuracy. Coverage is among all the tuples, all the observations, how many observations are covered by this rule. It may not be classified correctly, but how many has been covered by this rule. Meaning this data, this observation actually meets the requirements of the precondition. So those are covered rules, covered observations. Accuracy then, on the other hand, is among all those covered observations, how many were correctly labeled. So coverage and accuracy are two basic metrics to assess the quality of a rule. Yes, go ahead.
So when we have a decision trees, also to me it seems like it's similar thing, because when you're traversing the decision tree, you're going through these rules. So what's the difference? So
we'll cover that. We'll cover that in the next few slides.
I have another question.
Yeah.
Decision rules has nothing to do with association rules, right?
No.
There's nothing, no way to. Okay.
No. They are disjoint.
Okay.
Yeah. So as we defined, a rule-based system is just a set of if-then rules. It could happen that more than one rule being triggered by one observation. So this observation meets the precondition of multiple rules. If those multiple rules predict the same class, then there's not a problem. It's okay. However, if those different rules predicted different classes, then we have a problem. We need to resolve conflict. One way of resolving the conflict is, like what I suggested before, simply organize all those rules into a decision list. A decision list is not a set of if-then rules. It's actually if this rule, else if the other rule, else if the third rule. So you can only trigger one rule at a time. The rules are prioritized and listed in this order. The first rule that got triggered will be the one that determined the class label. This is one way of doing that. So the rule can be organized based on a number of different criteria. For example, decreasing order of prevalence. The most general rules going to get fired first, then those the rules that cover a small number of classes. It could also be ordered using misclassification cost. In a medical application, what's the cost of not diagnosis people with certain disease, and what is the cost of false diagnosis this person? So based on those costs, you can organize those rules in a meaningful way. Another way, yes?
Well, it was a follow-on question to the earlier question with association rules. And as also based on what you were saying with the sorting or prioritization of rules, is the primary difference then between association rules and here is that we don't have like a predefined class to say somebody is going to buy a computer or not buy that, like the final class is not defined. But if you took association rule and you like the market or like a transactions with item, and if you were looking at it such that let's say the goal was to decide who will buy toilet paper, then you're using the features as buying different products as your feature, and you're trying to predict toilet paper. Is that conversion of the association rule to a sort of a this type of rule-based system or decision tree?
I think you made a very good observation in terms of you don't have a class label to predict when you learn your association rule. You'll learn anything that co-occurs in association rules. And also the second point to make is the key here is what is the rule? How do we evaluate the quality of the rule? In association rules, we care about co-occurrence. In decision tree, we care about the purity of divisions. In this if then rules, we care about the accuracy and coverage. We want a rule that covers a lot of training examples, but also produce good prediction. Because our optimization goal is different, the things that we learn are going to be different. The rules that we learned are going to be different. The decision list is a way to avoid when multiple rules are triggered, then which rule get fired. It's solved by using this priority list. Another way of doing that is just having all those rules as disjoint. All those rules can be fired. And then when those rules are fired, then you execute your conflict resolution methods. So this one example is given here is size ordering. If one observation has triggered more than one rule leading to different classes, then we look at those rules and see which rule is the most strict, has the toughest requirement. We will fire that rule. Maybe that's because our example meets the most conditions of that rule. Maybe that rule is going to give us most accurate classification. So the rule is not fixed in a priority list. It's depending on when the rules are triggered. When the rules are triggered, then a resolution, conflict resolution technique kicked in to decide which class to predict. Questions? Or if then rule? Okay. So then we can talk about how to learn those rules. So as Saba mentioned, we have one clear way, straightforward way that we all know, is we can learn a decision tree and extract rules from a decision tree. That's certainly one of the way that if-then rules can be learned. So from this tree, we start from the leaf node going up, trace up, that gave us one rule. This path gave us one rule. Every path starting from the leaf node gave us one rule. Those rules are mutually exclusive, so you can't really trigger more than one rule at a time. And exhaustive, and all those rules, the data, the training example, all different possible rules are listed here for the training example. One thing to mention is when we build decision trees, we prune decision tree. If we have rules extracted from decision tree, we could also prune the rules by eliminate the leaf nodes and see after removing this leaf node, does the quality improve for this rule or not? I think I covered everything. Conjunctions, right, everything are and together as we have observed earlier. So this is one way that rule can be learned. Another way that the rule can be learned is learning the rules directly from training data. Many sequential covering algorithm has been proposed. The idea is we will start questions.
Yeah, I had a question in the previous slide. So I understand why by default it makes sense to make them conjunctions because each level that you do is sort of adding a condition. I'm wondering whether if there are certain rules that where you only have, say, one level, so you've got the parent, the root level, and then you add a level, whether you, and the outcome is the same, so student equal, by computer is yes, can we combine them using disjunct, like an or? Or is that not really the practice to sort of simplify by combining with an or?
For rules extracted from decision trees, it's probably not possible because every time only one rule can be fired. I mean,
right,
only one rule can be triggered.
So let's say in this case, we see like, the age between 31 and 40 and it's yes.
Yeah.
Right. And then let's say we had I guess it depends on after we run this decision tree, we have, more like other ways we're getting. So let's say in this case, we have age 31 to 40 is yes. Let's say we have another rule in this rule base that was if profession equals IT, then computer buys yes.
Yeah. See what we have here, age, yes. Student, yes. Credit rating, yes. So you can see those as all conjunctions when you have those rules enumerated one by one. I mean, not conjunction, disjunctions. Fire any of those conditions, any of those rules, you get a yes prediction.
Thank you.
Yes, sorry. Okay, so we can learn rules. Rules can be learned, so it's called sequential covering method. So we start from the very first rule, and when we learn the very first rule, we will make the rule very, very general, like if no condition, then long decision is accept. Then we keep on adding conditions to it to grow the rule. So rules are learned one at a time, from the most general to becoming more specific. When each time a rule is learned, we call this algorithm learn one rule. We're going to talk about learn one rule later. When each time this rule is learned, the tuples that are covered by those rules are removed. So then the next rule going to be learned on this fresh start from, again, the most general to the most specific, to become more specific, using the remaining tuples. We repeat this process until some termination conditions are met. For example, there's no more training example, or when the quality, we can no longer learn a rule with certain coverage and accuracy. At that time, we will stop. So the rules that we learned becomes this set of the rule-based system. So how then do we learn one rule? So as we hinted, condition at the initial step, the condition is empty. We want to predict whether somebody loan application will be approved or not. We start with empty condition. We add a new attribute. And so there's lots of new attribute, right? So we add one, and we see how does this one improve rules quality. If it improves rule quality, we keep this. We add another one using conjunction and see if this one going to improve the rule quality. We're continuing doing that until rule quality is no longer improved. That's one rule that we learned. We remove the observations covered by this rule and start to learn the next one. And now we talk about the rule quality. Then what's the rule quality? How do we, well, many rule quality-based quality measures, most of them based on the coverage and accuracy. One specific one used in the FOIL algorithm is called FOIL gain. The formula looks like this. Sorry. I'm still healthy, no virus. What does this formula tell us? It tells us that I want rules. If you look at this, this is the initial rule. This is the rules at a condition. So the prime is a new one. And we compare, if you look at this part, this is the accuracy. All the rules covered and correctly covered. So pos is positive. Neg is those rules are not of this class but being covered. So this is accuracy. We want new rules accuracy is greater than the old one. And also we want this new one has very good coverage. So we want a balance between coverage and accuracy. We want the rules that have high accuracy, but also cover many rules. So this is our rule quality. When we assess whether we need to add a condition to the current rule, we compute this FOIL gain to decide which attributes would add the most, adding which condition going to add most to the rule quality. The rule pruning, as we mentioned before, even when we learn one rule, not extracting rules from decision tree, there's still the need to pruning rules. Rules can also be learned with overfitting. So rule to do pruning idea is very simple. Compare the rule before removing a condition to the rule ahead of prior to remove that condition. But when pruning a rule, a different standard is used. This one is the formula. So the idea is you want a rule you want to make sure after the rule is pruned, you're not adding lots of negative or false positive examples. If this formula is not very, so what we can see this part again is accuracy, right? Adding negative basically saying that I will make I will try to find the rules that find the pruning strategy that punish negative coverage twice. If you don't see that, I think I wrote it somewhere here. So this accuracy, if we do this, and if we write it in a different way, it's 1 minus negative and the denominator. But this FOIL pruning is 1 minus 2 negative. So you can see a punish negative coverage more. That's why it's not using the accuracy. Yes.
Is positive, like, are we saying positive and negative? Are they just like a two-class problem, or positive? Sorry, I missed this part. Is positive just the ones that are correctly classified?
See the negative and positive. Oh, okay. I see how I see how this is not being written clearly. So a rule is covered. Rule covers something, classified it correctly. That's positive example. Negative is a rule covered something and predicted wrong. So predicted wrong label.
Okay, so positive then is like if you correctly number of correctly classified tuples is positive.
Yes.
And negative number of incorrectly classified triples. So then I think Sabah was wondering, is that then the same as precision?
Position, let's see. Position is among all the positive things that you recovered. How many are really positive? So among everything that's, if you think covered, I think this accuracy is actually position. This. So everything that's covered and how many of those are positive. This is position. This is not position. Right?
Thank you. And so essentially that way, like the other condition is sort of trying to, when you're trying to get the, is that like also trying to get the recall rate? No, maybe not.
I don't think we can draw a direct comparison here. If we consider everything covered being the base, then that's covered, then how many other rules are there? How many other examples with class are out there? And those is recall. Okay, recall measures among all the observations with this class label, how many you have recovered. The reason that recall is not a consideration in this learn one rule situation is rules are learned one by one sequentially. Even if there are other examples with this class label laying out there, we can divide new rules to cover those. We don't have to make this one rule cover everything. It's simply not possible. So in this case, we can say that our focus is getting the position right, but also with good coverage. Does that make sense?
Yes, thank you.
Okay, good. So we talked about decision tree and decision list last week, and that this is a time that we can summarize the difference. We mentioned before they have different we can call it optimization goals. The decision tree want to drive the nodes to become purer and purer. Decision list to look at rule coverage and rule accuracy. In general, they're going to learn different rules. Decision list rules are ordered because the rules are not exclusive. That's why we need to add if else into that to make it exclusive. Decision list can be more expressive. As we know in decision list, we have those replication and redundant issues that can make a rule long and hard to parse for human beings. On the other hand, the decision rules are exclusive. There's no two rules can be triggered by the same observation, so there's no conflict possible in a decision tree. People have also proved that for any rank R decision tree, R roughly you can interpret as the depth of the tree. With M leaves, there exists an equivalent R decision list. This means that decision tree collectively is a type. You can see a decision list. Decision list is more general. However, this doesn't mean that decision tree and the decision list algorithm are going to generate the same set of the rules. Performance-wise, it's hard to tell which one is generally better than the other, but decision tree is definitely much more well-known and widely used than decision list. So that's all we're going to talk about. On the popular learning algorithms, to review, we look at decision list, we look at Bayes